All right. So this is actually most of the material that we talked about last week, and I've just added a few sections beyond where we were. So, okay. So we were at logarithms last time, and so we talked about the telephone game, we talked about translation, we talked about the physicality of information, the relational structure, and fungibility. And we talked a little bit about invariance, in particular to a hole in a donut, sometimes known as a coffee cup. We talked about messages communicated to a goal or an observer, and the number of different types of messages gives you the information. And we eventually worked our way to duality between for logarithms. If you have a product of two numbers, positive numbers, then you can make another positive number by multiplying. On the other hand, you can take a positive number, make the logarithm of each, and you'll get two logarithms. But the logarithms are addition instead of multiplication, which makes it much easier to do multiplication. So I used to, in high school, I spent a lot of time with logarithm tables for doing calculations because it was so much easier. You look up the logs, add them, and then do them in the inverse. Okay, so we talked about what a logarithm is and what its structure is. And then finally, we got to the point of the logarithm stuff. That is that if you have m possible messages, then the information is, the Hartley information is log base 2 of that number. And that's basically using the idea of all messages being equally probable. This is the same kind of thing that Boltzmann did in his lecture, his paper on entropy back in the 1860s. And so we asked, what does entropy mean? And you can have it two different ways. You can think about the information I gain when I receive a message. Somebody's got their microphone on and you can hear it in the background. Please shut off your microphones as well as your videos. Okay, so the alternative is that H is the amount of information I lack before I receive a message. So it's a measure of the uncertainty about the message that I'm going to get. And there's many ways in which you can think about it. One of them is passwords. The reason that they are useful is because you are certain you know what your passwords are, but it would be hard for someone else to understand the what the message is if you make it more enough complexity. And so the other people are uncertain, you're certain. So that's how a password works. And and as I said, next week I'll discuss I'll discuss the insight that Steve gave, talk about surprise, and then move on to the other Shannon Insight communications channel. Okay, so now I gotta get the heck into, oh, sorry. I'm gonna have to somehow, let me, all right. Okay, so that's what I wanted. Okay, I'm gonna have to stop sharing so I can get in and change to a different one. Okay, we're moving into this set of lectures, and we're gonna do this in full screen mode, and then we're gonna go back and share the screen, and hopefully everybody sees the section 8B portion of it here. Oops. Okay. Okay. So as I said, we're going to do a little bit of insight into what Steve talked about last week, because I think he understood it and I understood it, but I'm not clear that everybody else understood it. Then we're going to talk about surprise and communications, and then move on to next week. Okay, we've gone through all of this material. As I said, I'm afraid many of you didn't follow what Steve said, so if I was wrong, we can skip this section, but we were talking about passwords, and the whole point of a password is that one person or only a very few people have it available to them. And if an unauthorized person were to try and access my email, invade my privacy, etc., how difficult would that be? Well, it depends, of course, on how many possible passwords there are. So if the password is a 4-digit number, which is what most PIN codes are, then there are 10 to the 4th or 10,000 possibilities. But an automated test, a computer test of that many possibilities would take a very short amount of time. It might be able to make 10 guesses each of the password of 1,000 different people and get lucky at least once. The entropy of the password is the base 2 logarithm of the number of possible messages. Measures how secure the password is constructed. So it measures the uncertainty of the knowledge of the potential intruder. So the entropy of 1 digit is log 2 of 10, or 3.32 bits. So a 4-digit password has 4 times 3.32 bits, or about 13.3 bits of entropy. And if you were to make it a little bit more complex, you might consider a password that was consisted of an 8-letter word. There's 26 different letters in the alphabet, or an entropy of log 2 of 26, or 4.7 bits per letter. So 8 times 4.7 is 37.6 bits. That seems like it's a lot better. If a computer cracks a 10,000 4-digit password in 1 second, how long would it take to crack 26 to the 8th 8-letter passwords? It would take 8 months. But would it? Passwords with random letters are hard to remember. Most of those 8-letter combinations are garbage. Most people choose a password that is a recognizable word. So how many 8-letter English words are there? Most people, when tested, can recognize and understand less than 50,000 words without a dictionary. And of the 50,000, approximately 8,000 from aardvark to zucchini have 8 letters. So the actual set of possibilities, the password entropy, is log 2 of 8,000, or about 13 bits. So our supposedly better 8-letter password is actually less secure than our randomly chosen 4-digit code, which was 13.3 bits of entropy. So that's why most computer systems, websites, etc., have special password rules. They have a minimum required length. They're required to include different types of characters, uppercase, lowercase numbers, punctuation marks. Sometimes the user is literally assigned a random password and forced to memorize it. That's why there are so many password saving programs, because when they come in, you got to put them someplace. So when you're going back there, you can't remember any of that. You have to go back to the password program and go and look it up, and then you can put it in. So even if I stick to fairly common nouns, there are about 2,000 of those, and another, say, 100 physicist names, I have an entropy of log 2 of, sorry, that's a typo, log base 2 of 100, or about 11 bits. A 4-noun phrase, a 4-noun phrase has a password entropy of 44 bits. So we could, instead of having a single word for a password, we could string 4 different 8-letter words, or etc., and put them together, and that's much more easy to remember than the random bits or random letters, because you can remember it. So the number of bits I need to represent a message from a source must be at least as great as the entropy of the source. And of course, I could use more bits than H to encode the message. There's no limit to how inefficient our code could be. but we cannot get by with less than H bits per message. Was all of this understood?
On the surface.
Yes.
Okay, good.
6%. But that's
You
my
want me to-
favorite. But that's my famous 6%, Bob.
I know. The question for me is, can we? I'm really trying to get you up to 15% at some point.
So is
Could
my wife.
could I ask you to say, repeat how Steve phrased all this last week? I mean, he didn't spend this much, time phrasing it. He said it very simply. What did he exactly say?
Oh, it was something approximately that, okay, if I had N numbers of messages and I wanted to know the entropy, I would have to take the log base 2 of all of those numbers, and that would then, and that needs to be the number of bits I need to represent a message must be at least as great as the entropy of the source. So it was something like that. I don't remember exactly. Do you remember it exactly, Steve?
Oh, let me see. I think I was giving an example to see if I understood what you were saying. And I think I picked as an example a password that was perhaps 10 characters long. And each character could be either a letter, a number, or some kind of a symbol. And I suppose there were 50 choices altogether. And if you picked them at random, how many choices would you have? And then once you compute that, which would be 10 to the 50th, I'm sorry, 50 to the 10th, then you take the log 2 of that and get the entropy. It's just
Right. Okay. Yeah. So I just took a lot more time to get into about that example because I thought it was good, but I wasn't sure that everybody followed it. So does everybody follow it now? Who doesn't? Okay.
I think there's some abstainers.
Sorry? Oh, you think there's some abstainers?
The concrete example helps. Steve's example actually succinctly put that way makes it, now why that's a limit, that's still, that's, you have to think through that, but that concrete example of the 50 different characters and the 10 letters, that does help sort out how you get to that number.
Yeah. Okay, good. All right. So, surprise. Hartley entropy, just as in the insight of Boltzmann and our lecture on Maxwell, used the postulate of equal a priori probabilities. Anybody remember? Not you, Steve. Anybody else besides Steve remember the postulate of equal a priori probabilities? And could somebody tell me what it is? I'll call a card here. Okay. Ernest, you want to tell me? Is Ernest in?
Okay, I'm unmuting here.
Okay.
I'm thinking that that means if you have X number of possible messages, then you, each possible combination you can come up with has an equal probability.
Yep. It's the idea that everything is equally, every kind of message that comes is going to be equally probable. And that, of course, is not reasonable. So why am I not seeing? I keep saying go back to this thing, and I'm not, it's not letting me. All right. Where? Okay, there we go. All right. Yeah. So the postulate is that every message is just as probable, equally probable, and that, of course, is not reasonable. We know that, especially in messages, if you're talking about an alphabet, E is much more probable than Q or X. So it was Gibbs who eventually created the proper definition of entropy. The sum of the P times the logarithm of 1 over P sub I. And in terms of the information probability, we have KB logarithm of 2 times the sum of P sub I log base 2 of 1 over P. So the most general case has the states are not all a priori equal. So why do I say that entropy is due in large part to the amount of surprise? Anybody want to hazard a guess? I haven't talked about it, so I guess nobody's going to hazard a guess.
I'm sorry, what is the question now?
The question is, why am I saying that entropy is due in large part to the amount of surprise?
Okay. Well, if you look at this definition here and look at 2 limiting cases, if there's no surprise, that means the probability of a particular I is 1, and any other I is 0. That's a definite a probability that one particular case occurs and the rest have no probability of occurring. Then if you put 1 for that particular I, you get an entropy of 0, which is what you'd expect if
you're certain. Yes.
You're certain. On the other hand, the other limiting case, if you equal a priori probabilities, you don't know anything. So you make the assumption that each one is equally likely to occur. Then PI becomes 1 over M, and 1 over PI becomes M. And when you sum that, you just get log of M, which is the uncertainty.
Exactly.
Definition.
Exactly. Okay. Yeah. So it's the fact that we don't have certainty that it is the surprise that is important. So suppose I show you a probability density function and ask you to tell me the places where they're very unlikely to be found, because we're now talking about unequal probabilities. So here is a beta distribution 2 and 5. The mean is 2/7. It has the dotted line going through it. And the probability goes from 0 to 1, and this is a probability density function. So what region of this would be a real surprise?
Greater than 0.8?
Yeah, greater than 0.8 and less than about 0.05 would be low. In particular, you can compute the credence interval, and I can ask, where is the region where x is less than some particular value x low? That is that the cumulative, for example, the cumulative density function is 0.025. And similarly, for x greater than x high, it's going to be 0.975. So this would be the credence interval for a 95% region. And this shows what the result is. So anything less than about 0.04, it has a very low 1 over 40 chance of occurring, and anything over 90 over 0.64 is also 1 over 40, starts out at 1 over 40 and gets even less as it goes along. So if this is not a region of surprise to you, then we could, rather than doing what we did, we could have a 99% credence interval. And that shows here 0.5% down, it looks like about 0.01, and the 99.5% region is from 0.75 to 1. So you can define what you think to be very uncertain. Now, in this case, there's only 1 over 200 chance that x will be found between 0 and 0.02. And similarly, there's a 1 over 200 chance that it'll be between 0.75 and 1. So we could have a discrete approximation to this because it makes it a little easier to work with the numbers. And I created a approximation to the beta distribution using maximum entropy, of all things. I'll talk about that sometime later. By the way, does everybody remember the Dirac delta function? Does anybody not remember the delta function? Okay, Bob Lukowski, would you explain what the Dirac delta function is?
It's a function that's 0 every place except when the argument is 0, then it's an infinite. And if you integrate over it, you get 1.
Okay. I was pretty sure you knew the answer, which is why I chose you. Anyway, so the next slide shows the probability density function of the approximation I did, and shows and following that, the cumulative density function, both the continuous and the discrete approximation. I've also thrown in the 95% credence interval um, to find out what happens in the discrete approximation. So these are the probabilities that have the same, have several moments exactly the same as the beta distribution. And I've had 22 points here. The two at the very end are so small that you can't show the arrows. The arrow just points to where they are at the bottom in the discrete approximation. So we can ask for what is the probability for x being between 0 and 0.2, and you go up here and it tells you that there's a 0.3%, a probability of 0.3 that if you measure something, you'll get anything between 0 and 0.2. So that's how you read a cumulative. We talked about this in the past, but I'm just refreshing your memory. So the PDF I showed you before has this black line as its CDF, cumulative probability density, and the approximation that I gave, showed you, has these stair steps because at every point you just add the next probability and then it's constant until you get to the next place, etc. Now, the purple lines here show, I don't know if you can see it here, but this has got a little purple line that goes here. So the 2.5% region just contains 1 point, and the 975%, actually you get this one, and there's another one in here, but you don't see it because the line is so thick. So I'm going to show you another, whoops, that wasn't what I wanted to do. There. Okay. So the line's too thick to see the small changes in 0.65 to 1, so I've blown up the region from approximately 0.9 to 1 in probability. And you can see that there's a little extra jump up here that you couldn't see in the previous one. And the purple shows that you have this point and that point. So there's two values in the discrete approximation. So why am I doing this? Well, I want to show how the value of the probability of each x sub I shows you the probability, the log of 1 over the probability, and the component of the entropy, that is the probability times the log base 2 of the probability. And usually the really surprising ones have an entropy component that's about 10 times the probability value. So this first one at 0.002 has a probability of 0.015, but when you take the log of 1 over that probability, it's 6, as opposed to most of the others are all 4. And so this, although not equivalent to these others, is about 10 times the probability value. And similarly, at the other end, the probabilities are 0.98, I'm sorry, 0.001 and 0.0003. And when you take the logs of those are 10 and 11. And therefore, the entropy component is about 10 times what the probability is. So these are measures there. All of the others are all about the same at 0.2. These are smaller, but they're considerably larger than the probabilities, as of course everything is. Okay, so I've gone over lightly for Shannon's entropy, and next I'm going to talk about messages through communication channels.
I think I have a question.
Okay.
If I can phrase it. Okay, assuming you have a hacker with a computer attempting to hack your password, and using these probability postulates that you've laid out, the computer would, I assume, for each bit, or each bit represents a number, a letter, or a character, or a symbol. So for each bit,
well, each bit doesn't, but a selection. You always
okay,
you have to have enough bits to be large enough for the size of the message.
Okay.
So if you had, before we had shown 27 alphabet, and we took log base 2 of that, and that allowed us to use, it was less than 5 bits, so you could use 5 bits to cover the alphabet.
All right.
5 bits
Regardless
for each
of,
character.
Sorry?
5 bits for each character.
Yeah, 5 bits for each character.
right, okay, regardless of how many bits you need to create a particular character, your hacker is attempting character by character to figure out your password. So
Actually, most of them don't. Well, for the PIN numbers, yeah, that's true. But for the words that people usually use for passwords, people have lots of tables that have been created over time that tell you the probability of the frequency of those words in the English language. And so they actually use the table of most likely to least likely words you're going to come in. It's not doing it one character at a time.
okay, that's what I figured. So it's starting with the highest probability of word or letter, whatever it's looking for, and working its way down to the lowest probability.
Right. Right.
Okay.
Great. Thank you. Okay. All right. So we're now going to move on to communication channels. So suppose someone sends you a 1-bit message. What does it mean to receive half a message? That might seem like a strange question. A 1-bit message looks like it should be a single atom of information, or 1 or 0, yes or no. So can somebody, let's see, let me go pick somebody here. Who am I going to take? Adrian, are you on? Would you unmute if you are and let me know? Okay. Kathleen, would you unmute? And what do you think it means to receive a half a bit of a question? All right, I have to do it this way. Okay, she's not on, sorry. Okay, Ray, could you give me some insight into the half a bit reception? Can you guess about anything?
It seems to indicate that you have a lot of uncertainty still, but I'm not sure I can clarify it beyond that.
Okay, well, that is indeed true. And let's see.
I'll take a guess.
Okay.
In this way, you're attempting to compare a bit to an atom, or hypothetically, and of course, an atom is not the final say. An atom is made up of smaller parts. So what I'm guessing is a bit is also made up of smaller parts.
Well, that is an accurate statement, but it's not the reason. So let me.
The only thing that makes sense to me is you're going to have to talk in terms of probabilities. For example, the probability that the bit is a 1, maybe 3/4, and 0 is a quarter. You're not certain what it is, but you don't have 0 information. You have some probability of one versus the other.
Yeah.
If I could make a suggestion.
Yeah.
I'm thinking that half a bit would be, instead of a yes or a no, that you have received a message. So you have a bit of information, but you don't actually have the yes or the no.
Well, that's basically it, but we'll go through an example. So if I send a message with many bits, you could think of receiving the first half of them or maybe the last half of them. But how on earth do you receive a half of a single bit? Well, let's go back to our original story about communication between Alice and Bob. Alice has been asked a question, which is a yes/no question by Bob. And Bob is patiently waiting for her answer. The two possibilities are equally likely, 0.5 for yes and 0.5 for no. So the entropy of the message is 1 bit. Bob lacks that amount of information before Alice speaks. It is how much entropy he'll gain when he hears and understands her answer. And Bob has studied Edwin James and Bruno Di Finiti, and he knows he should be a Bayesian probabilist. Alice and Bob are standing in the middle of a noisy party. And in that kind of an environment, it can be very hard to make yourself understood. After Alice gives her answer, Bob is not entirely sure he hears it correctly. He thinks she said yes, probably she said yes, but he isn't quite certain. So Bob updates his prior probability, which was 50-50, and his posterior probability is 90% chance of yes and 10% chance of no. So because there was noise around, it made it hard for him to hear it correctly. And he was pretty sure he knew what happened. In fact, after he updated using Bayes' law, he found out that his posterior probability was 90% certain of yes and 10% chance of no. So after Alice says whatever she says, based on what Bob heard, his uncertainty, as I have said twice now, 9.9, and for yes, and 0.1 for no. If Bob later learned that she said yes, he would not be very surprised. And if he later learned that she said no, his surprise would be greater. Bob still has some entropy even after Alice spoke to him. Her message for Bob, still uncertainty. Bob still has uncertainty about her answer. So, applying Shannon's entropy rule, entropy formula, the entropy remaining is the average surprise. So Bob started out lacking 1 bit of information, and Bob still lacks about a half a bit. 0.9 log of 1 over 0.9 plus 0.1 log of 1 over 0.1 is 0.137 plus 0.332, and it's 0.469, roughly a half a bit. So is this clear? Is there anybody who doesn't understand what we're talking about here, about why Bob still has uncertainty, and how you compute what the number of bits he still is uncertain about, is his information? Okay. I'm going to assume everybody is. Art, are you following what's going on more than 6%?
Bob, this is kind of interesting. That implies that even though 1 bit was sent, because she did either say yes or no, based on a perceived uncertainty due to noise, he only got half a bit.
Correct. That's exactly correct. At the beginning, we define information as the ability to distinguish reliably between possible alternatives. Bob has certainly gained some ability because he's a Bayesian and he updates his probabilities. Some information has been obtained about which answer is Alice's, but he does not yet do, he doesn't have the ability to do it with perfect reliability. So that is another aspect of what's going on. Somebody got a question?
You have to have some, between the sending of the bit and the receiving of however much has been received, less than a bit, you have to have an intervening factor. And in this case, it's noise.
Right. That's exactly correct. So noise produces ambiguity or uncertainty. And we're going to have a picture that shows how there's 2 parts of our process in information. One is the collection of messages that we're starting with, what we're trying to get the answer about. And they've been encoded into some kind of a signal. In the Alice and Bob example, Alice used her voice to speak to Bob, but it's a signal, a physical process that may have distortion or noise. And we were in a party, so we had noise. Our receiver gets the signal, decodes it using the coding of our referent to produce the observer's received messages. Now, these, of course, are not perfectly accurate, but they still can decode what's going on. So this is the picture. You have a referent here. This is your messages. In this particular case, we've got a newspaper. You make it into a signal. There may be signal distortion. There may be noise due to the environment, etc. And at some point, there's someone who collects that information. So in a digital system, you have a signal processing, a digitization, error correction, decoding. And we're going to talk about error correction next week, not this week, but this is the basic process that we're talking about. So one of the things you need to notice is that there's two pieces to this. There's the collection of messages that is being sent, the referent B, and there's a signal that is sending the referent material to an observer. And all of the stuff that happens, the signal processing, digitation, error correction, and decoding, all of this stuff happens to the signal only. So, yeah.
But one thing that does exist is the referent does know what bit they sent.
Yes.
Alice. Okay, so if Alice, so somewhere along the line through all this, the information hasn't been lost. It's been lost in the transmission, but whatever that original information still exists in its form in whatever whatever the referent means, whatever that means. That information is still valid in that entity.
Right. And in point of fact, the very simplest error correction would be simply what we do in Ethernet. When you have a packet of information that is doesn't arrive where it's supposed to be as it's being moved through the Ethernet, it just goes back and says, hey, send it again. I didn't get it. Send it again. And it keeps sending it until it gets it. So that's the simplest form of error correction. You simply ask the referent to send the message again because you didn't get it. Or you had so much error that you're unclear about what the message was and you asked for it again. So if you only got maybe 1/100th of a bit, you should probably resend it or something like that. Anyway, so the key point on this is that all of the stuff that happens to the signal, not the referent. As you pointed out, the original sender has the information exactly still. So that's important. Okay, so the received messages may not tell us with 100% certainty about the transmitted message. Some information has been lost. Possibility of error has been introduced, and noise is just ubiquitous in any kind of communications channels, more or less. So there's no communications channel for information transfer or any medium of information storage that's totally immune from error. If you're talking about electrical signals, thermal motion of the electrons produces tiny fluctuations in the signal. Paper tapes get torn or damaged. Distant thunderstorms or sunspots produce radio static. And even printed books have typos. So how do we take noise and error into account? Everybody follow what's going on here? If there's any questions, please ask. Okay, so how do we communicate in the presence of noise and still avoid errors? There are some of the most important questions in information science. They are the very questions that Claude Shannon explored in his paper in 1948, which established the foundations of information theory. The answers he developed are surprising and remarkable. Shannon introduced the concept of a communications channel. This refers to a physical process to convey information. So you have something between an input and an output. For instance, a long electrical cable can act as a channel, and a fiber optic or a radio link or sound waves through the air could all be channels. My desk drawer could be a channel. Anybody want to tell me why a desk drawer is a channel?
Because you can put a message in it and then at some other time take the message out.
You got it. Thank you.
You're welcome.
Yep, I write a phone number on a piece of paper, stick it in the drawer, and then 6 months later, I take it out and read it. And so, although I knew the number initially, because our memories are not perfect, and in fact, usually degrade over time, I have to go and look it up again. So the concept of a channel is not simply about carrying information from place to place. It also, I hope you're all able to hear me because I just got an insight that the internet is unstable for me.
You froze for a second, but you're okay now.
Okay, great, thank you. So it also represents the storage and retrieval of information. Over time, for example, your memory is a channel. And if the output were always exactly the same as the input, then the idea of a channel would be a trivial one. But that is a rather unusual situation. What the channel does is establish a relationship between the input and output. And for each possible input, the channel determines which outputs are possible, what the likelihood the outputs are for each possible input. So to analyze a channel, you also use probability. The input is an information source, which we're going to call B, our referent B, whose probability distribution over the messages is P of B, where B is this collection of all possible messages. And the set of possible outputs we're going to call A, and that's where each of the outputs of A, and assuming it's a pretty good channel, then the outputs should be a subset of the inputs. For some channels, the output is exactly determined by the input. But for many other channels, they act in a much less predictable way. So several possible outputs might be the result of a single given input. To describe the channel, we need to describe the rule by which the inputs lead to the outputs. That rule is specified by conditional probabilities. So you have a probability of the outputs given each of the inputs. So all of the output possibilities are in A and all of the inputs are in B. So you have to understand the likelihood of each of those. The big lesson here is that a communication process, a channel, involves both inputs and outputs, and they're related to each other, but not necessarily identical. So as a sender, I know the probabilities of the message and all of the various possible inputs. On the other hand, the channel determines the conditional probabilities, the probability that the output is, out of all of the possible set of outputs, for each of the inputs. If you remember our section on probability, the conditional probability is that the conditional probability of A given a particular B is the probability of the joint probability of A and B divided by the probability of B.
Bob, I have a question if I could.
Sure.
I'm not quite sure what to make of the following. So I, as the sender, know the probabilities, P of B for any given B and B in capital B. What is that saying? That it can't be saying that I don't know what I'm sending with
No, but you have a collection of messages that you can be sending to somebody.
so
And the probability of each message you're sending, that some are more frequent than the other. And
okay, that's what
that's what the P of B is.
I got you.
Okay. So, okay. So the conditional probability, which tells you the relationship between the outputs and the inputs, is simply the joint probability divided by the probability of the messages. So we already talked about what the joint probability of distribution was. That is, it's the probability of B times the probability of A given B. And if you have a probability of input-output pairs, it's just the probability of the input. If it's independent, it's the probability of the output given the, oh, I'm sorry, no, the conditional probability, it's the sorry, I didn't get this clear. Let me show the picture. It's easier to see. Okay, we have two random variables from the information or communication theory point of view. You have a referent, B, a collection of possible messages that are being sent. You have a signal, A. That signal is potentially got, it certainly has the information about B, but it may also have some type of distortion or noise. So A carries the information about B. So this joint probability of A given B is shown here in a matrix, assuming that it's dependent. So the information resides in the correlation of A and B, the joint probability. And if it were exactly, if it was perfect, then A would be 1-to-1 with B, and 2 with 2, and 3 with 3, etc. But there is some possibility that if he sends 1, might get 2, or it might get 3. So the information resides in the, for the communication channel, the information resides in the correlation of the outputs and the inputs. And in communication processes, only A, the channel, is affected by operations. So there may be another more subtle way of describing the communications. Most channels are mass produced, and so standard channels may be subjected to a series of tests for the desired inputs and outputs. And so our tests may be represented in another probability distribution, as we've been talking about. Suppose we know the joint probability of the channel for our set of inputs, B. There may be another probability, conditional probability of an incorrect output. So given A, now we're talking within the channel, the probability that the outcome A is actually A prime. So the output mechanism, the collection of observer measurements of the signal, may change the signal to an improper set of outputs. And I've called this local A operations, local channel operations. So we have the probability that given a referent B, instead of getting A, which is what you would like down the middle of the diagonal here, instead you get A prime. So we had been computing P of A and B, the joint probability of P and A and B, but we also can, by using the information that we know about how it works, what the probability is that each of the different outcomes gives a mistake. That's what K of A prime given A is. So the probability of a mistake given a particular input B is just the sum over this probability with this probability that we talked about previously. Is everybody understanding what it is that we're talking about? Lee Gale?
Yeah, I want to ask about the mistake. Are you talking about a natural mistake such as noise caused mistake, or are you talking about a mistake, a man-made mistake such as a hacker, or both? Are you talking about both?
Well, typically in the example that I was talking about, where we're dealing about a signal channel that is, mass created and can be tested, we're talking only about the mistakes made by the channel. But you could also, using your own prior probability of what an intruder or someone else would be, but we'd have to add that on to another signal similar to this, but due to that other impact. This one right now is simply talking about what the channel is, how it makes its mistakes.
And when you talk about mass produced, apparently you're indicating that the channel is defective in some way.
All channels are defective.
Oh, I guess, oh, yes, you did say that earlier. I guess what I'm saying is the mass produced channel is more defective.
No, not more, just all channels are defective. A mass produced one is one where somebody can go take a standardized one, put it in a laboratory and make tests on it. And it is the ability to test for various inputs what the outputs are. And so you can, in essence, determine this probability from an experiment as opposed to just from your experience.
Bob, I have a question.
Yeah.
I'm not sure at this point I can cleanly separately define what each of those two factors are representing in that formula you have there, the P, A, comma, B, and the K, A prime A. The P, A, comma, B, and the K, what segments of the process do they represent?
Okay. So the P of AB is this one, where you have a referent and you have a signal and you have a correlation of A with B. This is a process that, if you're thinking about Alice and Bob, it's the noise in her voice being carried to Bob. So this represents P of A given B, I'm sorry, P of B, P of A and B is the probability that Bob updates to give him what his probability of the result that Alice gave him. So in the example, they haven't got a channel that they've been able to do experiments with, so they don't have any information about whether or not the signal she sent was reproducible. Whereas in a communication channel like a wire, you can test how frequently you make mistakes for any given input, and that's the K portion. So this represents the ability of a machine or a person or an observer who gets the results, but they know the relationship between the messages coming in and the results coming out. Whereas this represents a process that allows you to give a structured information about how the channel works under standardized conditions. Did that make it clear?
So if K A prime A were a Kronecker deltas, that is 1 if A prime were equal to A and 0 otherwise.
Yeah,
So
that would
there's
be
no way-
another diagonal down the center
Yeah.
here.
Um,
So you have two ways of getting the signal. One, there is noise and somebody observes it, but you may also have more information about the channel than just the reception that you've gotten in a particular message. So this represents the uncertainty of the message for a particular message. This one tells you the information about how the channel operates over all of the possible outputs.
Okay,
Okay, great.
thanks.
Everybody got that? Lukowski.
I'm okay
Okay,
with it.
okay, okay. I'm going to ask you a question then.
Okay.
Go back to A and B. If you've talked both about people communicating and about the system, this hardware or whatever it happens to be. In the case of the room, it's just air that's transmitting the acoustic signal when they're trying to talk to each other. But if you had two people and you had a telephone system, I could see where all the electronics, the wires, everything else, is that where K is wrapped up in? Or is it in the people? Or am I?
No, it's in the wires, and because you in a current telephone system, it's not wires. It's,
Yeah.
it's digital signals, and there is, for any particular set of bits sent to you, there is some probability that you're going to get the wrong set of bits. And you can actually go into a laboratory and you can take Wi-Fi signals, or you can take Bluetooth, or you can take whatever you want to take and actually test to get for a reasonable set of inputs what the frequency of the actual outputs are.
So that's K.
That's K.
Got it. So the case kind of, at least simplistically perceived, kind of the hardware aspect, the thing that has to do with physics, that part of the physics. The communication part, particularly when you put the people involved, there's very many other systems involved between the people perceiving the message and hearing it properly, and even their audio systems. So their hearing systems is probably more tied up in P?
Yes,
Got
exactly.
it. Thank you.
Bob, let me see if I can rephrase it to make sure I'm understanding it. The K is a property of the wire, or whatever the channel is.
Channel is, right.
That's been measured. The P might account for noise arising from a sunspot.
Right.
Something that you're not going to measure in the lab, but something that can happen in that process of communication.
Correct. Correct.
Okay.
That helps.
Yes, it does. Thank you. I really appreciate that.
Okay.
Good. Okay, these collection of observer measurements can, or receptions, can be of two different types. First type misdirects the output measurement from the desired outcome, A, to an incorrect A prime. This is simply a set of permutations of the signal measurement outcomes to a different measurement outcome for every one of the outcome possibilities. So these are row permutations within here. So you can, in principle, make them reversible. You can, especially if you know what's going on here. However, the other type of changes are called blurring, and they're not reversible. So both of those two types of changes can occur and are in the conditional probability K. So there is part of it that's reversible in principle and part of it that's irreversible. So as we keep saying, the Shannon measure of information is the entropy, the average surprise. The input has an entropy H of B, which is the total amount of information in the transmitted message. The output of the channel also has an entropy H of A. And the combination of the inputs and outputs have a joint probability and correspondingly a joint entropy. So there's a useful fact about entropy. For any two variables with any joint probability, the joint entropy is no larger than the sum of the individual ones. So now I think this is pretty intuitive. The information in both variables can't be larger than the information in one plus the information of the other. Of course, it might be less. If the input is a 1-bit message and the channel is perfect, the output is always exactly the same as the input. So H of B is 1 bit, H of A is also 1 bit. But since knowing B automatically tells us A, H of A and B is also just 1 bit. And this is much less than the sum of H of A and H of B, that is 2 bits. So can we ever have a joint entropy equal to H of A plus H of B? Yeah, if the two random variables are totally independent of each other. Somebody, Art, are you still on the line or are you off? Let me take a look. No, he's left. Okay. Chaz, why is totally independent random variables such that the joint entropy is equal to the sum of the two entropies?
Bob, I'm not following this very well.
Okay, well, if you remember, whoops, hello. How about going to the next slide? Okay. The probability of a joint distribution, A and B, if they're independent, is simply the product of the probabilities of A and B. And since you take the log of those two probabilities, you get the sum of the logs, and the log of those probabilities is the entropy. So if they're completely independent, that is, if the receiver knows nothing about the input nor about the output, sorry, this should be an A, the observer or receiver knows neither what is sent nor what is received. So the amount of information that the receiver lacks at the outset is the probability of both of those, and the corresponding joint entropy is the sum of those two logs of those probabilities. Is that clear?
Yeah.
Okay, great. So can we ever have the joint entropy? I just did this. I must have gone the wrong direction. I apologize. Yeah. Okay. So that's as far as I got this week. So next week, we'll discuss different types of communication channels. And then we'll move on to coding structures that prevent the loss of information, and hopefully maybe even more. So thank you.
I want
Yeah,
to ask you about something that you kind of glossed over pretty quickly, and that was blurring. Could you tell us a little more about blurring that is irreversible?
okay. If you're simply shifting messages around and you know roughly which one is occurring, you can always undo it. You can find the inverse permutation. That's straightforward mathematics. Now, you may not know which one it actually came in, but if you do, you can undo it by finding the inverse of the permutation that created it in the first place. But blurring means that you're not simply substituting one outcome from another one. You're changing the probabilities on all of them to the other one. So when you are uncertain about what is the relationship between A and A prime, that is, if you don't know that what kind of a relationship that is, that's blurring, and if you don't know, you can't undo it. Did that make more sense?
Yes.
Okay.
Thank you.
Sure, not a problem. Okay. Okay. Any other questions?
No, well done. Although I do have one quick question for you. Go back 2 slides. Okay, that slide right there, where you ask us a question and you say why. What do you see on the bottom of your screen?
I see a lightly grayed out answer.
Yeah, so do we.
Yeah, I know.
Oh, good. Okay, I was just wondering. I was going to ask the question. The answer is always there. I was always curious whether you were not seeing that or we were seeing the answer. So I was just trying to help.
Yeah, no, I do that so that you can, you know, at least if you read ahead, you'll be able to figure out what the answer is.
Well, that was it. I always thought I was being asked a quick question and I was being given the answer, and I felt silly. so okay. Well, very entertaining again this week. Very useful.
Well, Bob,
Okay.
thank you very much for all your work. That's been educational.
I'm glad.
Thanks, Bob. I thought it was fascinating.
Yes,
Great.
thank you.
Yeah, we're just going to do a little bit more on the communication stuff, and then we're going to switch to the Slizard engine and Maxwell's Demon and get to the hard part, which is the IDO states and what they mean in terms of how you can actually create thermodynamics strictly from information. So, and hopefully you remember Landauer's principle, everything in information is physical. And so we're going to move on to that. Hopefully, maybe even start in next week, but if not the week after. That's what my goal is to get to.
You know, I was thinking as you were lecturing about how I view this probability or trial and error process. Every time I dictate something into my cell phone, you can watch as the words come on, the computer trying out different possibilities. And sometimes it'll flip, one word to a different word, back and forth, seeing, which is the greater probability given that context.
Right. So, yeah, it's all about probability. It's all about Bayesian. How you use the information you get to update your probabilities of the outputs. So, okay. Thank you, everybody. And I'm going to have to call it quits now because that's all I did this week.
See you next week. Thanks again very
Thank
much.
you.
Sure.
See you
Thank
next
you.
week.
See you next week.
Thank you,
Bye-bye.
Bob.
Wait,
Bye.
bye.
Okay, stop share. And I'm gonna end the meeting.